welcome dear students. We are discussing the quantum technology, and in this series we are discussing the quantum batteries. So, for the quantum batteries, charging, discharging and the state is very important. So, the charging discharging phase of quantum batteries are dynamic process that can be specifically controlled to enhance the device figure of merits. So, the quantum batteries depend upon its fast charging and slow discharging, and storage time should be higher. Moreover, it should not be self discharge. So, these are the some of the basic points of the quantum batteries. To the same, various approaches have been proposed which include the exploration of the non-reciprocity, and that is through the basically just that is a squeezing effect, virtual photons, catalyst shortcuts to adiabatically optional quantum control among the others. These are the basic points. So, a particular implementation of a quantum energy storage device is the Dike quantum batteries. The name Dike was attached to this proposal precisely because of the quantum battery is composed of the n identical TLS coupled to the very same photonic mode of the cavity. Like this model indeed describe the interaction between the an ensemble of emitters and a common radiation field. So, these systems feature interesting properties such as superradiance, which is a collective phenomena where an ensemble of interacting excited emitters decay much faster than one in which the interactions can be neglected. So, this result in an enhanced radiative decay rate and the super extensive scaling of emission intensity growing with the number of emitter as n square rather than n. So, superradiance originally demonstrated in the context of atomic and the molecular physics. So, that has been observed in the various solid state system such as molecular H aggregates. Moreover, we are having a quantum dots, organic single crystal, single diamond nanocrystal at the room temperature and the color centered in the diamond. So, for practical implementations of a solid state quantum battery, TLS can be realized by using any material that enables the realization of the quantum system with a discrete energy spectrum containing a ground and a excited state, well separated by the rest of the spectrum. So, the example that include must be not limited, but the quantum dot spin system such as nitrogen vacancy we can take as a center in the diamond, and superconducting qubits such as the transmons, and interest in this type of quantum battery is mainly related to the potential ease of the experimental fabrication in the solid state devices, where we are having the spin system such as nitrogen vacancy centers in the diamond, but in the solid we are having. So, experimental fabrication in the solid state devices. A recent example being that the organic molecule in the Fabry-Perret cavity. You can see that is the Ferrero et al. Calculated the maximum charging power for the n identical particles, each composed of the TLC coupled to the cavity mode and operated in the parallel, as well as that is the quantum battery with the NTLS. So, we can have this type, we have these are the centers where we are having the various points where we can have this is the schematic illustration of an array of the quantum battery operating in the parallel each battery is made of TLS, that is the energy separation between the ground and the excited state, that is defined by the H cut omega naught, coupled to a separate photonic cavity, that is defined by the blue. Here we are having the blue cavity where we are having the energy excitation from ground to the higher level. So, this is the basically the term collective charging has a clear advantages in exhibiting a charging power higher by a factor root n of compared to the parallel charging setup. So, further studied revealing that the enhanced charging power of the quantum batteries originates from the many body collective effect rather than the purely quantum effect. That will be used the many body quantum effect. So, we are having the red arrow that indicate a transition from the ground state to the excited state induced by the photon effect, and that are simultaneously going. So, this is the photonic effect. So, now that illustrates the quantum battery. You can see on the screen, that is a quantum battery for which an ensemble of the TLS is embedded in the same cavity and interact with the same photonic mode and reproduce with the permission. So, that data has been taken from the various research papers. So, other physical systems have been designed and theoretically studied for the implementation of the quantum batteries. One of the example that was an ensemble of the interacting spin system have been investigated in the framework of the condensed matter physics and the quantum communication and the quantum computation. So, this is the variation at the variance of with the quantum batteries. Direct spin interaction play a vital role in the spin batteries, that is that have taken in the quantum batteries. There is a direct interaction between TLS are neglected, while effective interactions between the TLS and mediated by the common cavity mode. So, the system based on single photon have been used for experimental simulation of the various charging protocols of the quantum batteries with aim of investigating the role of the coherence and entanglement. So, the effect of the catalyst interposed between the charger and the quantum batteries and the charging by indefinite causal order. So, what are the advanced material for the quantum batteries? What type of material we can use for the quantum batteries? There is an experimental implementation of the quantum batteries. Several characteristics are used for the material and the device architecture. It should be carefully evaluated for the quantum batteries. So, a critical feature is the energy difference between the level of considered material, means the spacing between the levels, that is the del A bandwidth. So, a critical feature is the energy difference between the levels of the considered material, that is the level spacing, that is defined by the del E, that is the TLS. The values significantly exceeding thermal energy at room temperature, which is about 20 milli electron volt, are less sensitive to the relaxation phenomena. Similarly, in excitonic systems, the exciton binding energy should be higher than that of the thermal energy, for it remains stable at the room temperature. So, a higher quantity factor, a higher higher quality factor Q, that is the quantum in the quantum battery of the cavity, is also relevant to enhance the interaction between the TLS and the electromagnetic field of the microcavity, as well as the tunability of the cavity. That material properties by external field in order to implement the different charging and discharging protocol. Other critical feature for the material selection is that capability of storing the energy for the longer time intervals, and availability of the material processing technologies that can be easily scaled up. So, different material platforms have been proposed for the experimental implementation of quantum batteries. So, there are the most promising ones, materials that are used. About its features, it is very important for the faster charging and the less discharging, as well as the storage time should be more. So, quantum batteries implementation can be make efficient by choosing the material. So, after presenting the properties and the structure of the proposed Fabry-Perret microcavity, there are the other organic molecules that are used for the excitons and proton coupling in the microcavity. Moreover, there are the potential inorganic semiconductors and perovskite materials that couple to the Fabry-Perot microcavity, that emphasizing collective phenomena and exciton phenomena coupling that might be useful for quantum battery design and fabrication. Apart from that, there are the superconductor circuits with the single and few qubits coupled to microwave microcavities. So, that materials can be used as a spin arrays for realization of the quantum batteries. Finally, the properties of the strange materials as a potential platform for the implementation of the quantum batteries that display a genuine quantum advantages. So, for information on other system currently investigated in the quantum technologies and potentially usable for realization of the quantum batteries, such as trapped ions, Rydberg atoms, ultra cold atoms, and the post-Einstein condensation. All these will be used for the preparation of the quantum batteries. So, one by one we will discuss. First is the organic microcavity. Organic microcavity is the one of the platform for the implementation of the quantum batteries that relies on the microcavities enclosing an ensemble of organic molecules. Organic microcavity, that is the organic molecules. So, Fabry-Perot resonator is typically used as a microcavity architecture, and it is formed by a layer of organic material sandwiched between the two high reflecting plane parallel mirrors. So, it formed a layer of organic material that is sandwiched between the two highly reflecting plane parallel mirror. So, mirrors can be thin metallic films. That mirror which you are using must be of the metallic film, and that must have a very less thickness. So, that distributed Bragg reflection, that is why it is DBR, Bragg's reflector, or the combinations of them. So, we can see on the screen that here we are having a metal mirror both the side, and in between that we are having that is a schematic illustration of a different Fabry-Perot microcavity with either metal or DBR mirrors, and as well as a combination of them. So, just we combine these in this form so that can be generate or can be stored the more photons. So, DBR are one dimensional photonic crystals, and that consisting of a stack of the NP, that you are just seeing the stacks of the basically stacks of NP pairs of the alternating layers of the high N, HN, high, low NL. You can see here there is a vicious stacks, the lower one and the upper one metallic layer are attached with it. So, that is reflecting index materials with the minimal absorption, in which the constructive interference among multiple reflections generates a broad band with high reflecting, that is the stop band, for light propagating along the stack direction. So, the light is propagating in the various stacks that you can see on the screen, that light when it is just propagating in the various stacks, so we can have this type of the band here. So, that is a photonic crystal. So, this photograph at different DBR mirrors with the stop bands in the visible and near infrared made by the reactive electron beam deposition. So, the cross-sectional scanning electron micrograph of SiO2 or TiO2 DBR, because here we are taking the various DBR. So, the transmission spectra of the DBR with lambda SB in the interval of 425 to 850 nanometer. Here we are having 425 to 850 nanometer, and that is the UV to infrared. So, we can have the visible to infrared region. So that is also taken from the sources. So, highest reflectivity at the central wavelength of the stop band is achieved in the lambda by 4 configuration. So, this scheme is implemented with the thickness of the high like TH and the low, that is the TL refractive index material. So, we are having the formula TH is equal to lambda SB divided by 4 NH, and here similarly TL is equal to lambda SB divided by 4 NL respectively. So, typically pair of the materials employed for DBR in the organic microcavity, you can see on the screen there are the various material which is the glass, and there is a silicon dioxide. So, and we are having the MgF2 ZnS, moreover CaF2 ZnS, and aluminum arsenide and gallium arsenide. We are having the various zircon materials. These are the various materials which can be used for the DBR. So, DBR can be fabricated by the different deposition techniques, including either the physical or the chemical vapor deposition, electron beam evaporation, molecular beam epitaxy, or the sputtering deposition. So, by layer we can deposit the DBR material, and that will form the just a cavity, microcavity. So, it is worth noting that the reflectivity of the DBR can be negatively affected by the bulk and the surface inhomogeneities of the deposited layers. So, by properly engineering the deposition processes, layers with root mean square roughness must be less than 2 nanometer and can be deposited one by one, and the reflectivity exceeding 99% is achieved for NP greater than 10. Number of deposition must be greater than 10. So, recently that has been defined the hybrid metal DBR mirrors made of thick silver layer coated with a few SiO2 and B2O5 lambda by 4 pair, and these hybrid mirrors allow for achieving the broadband reflectivity and enhance the confinement as well as simplifying the fabrication method. So, you can see here that is the hybrid mode where we are having the various, and that can increase the that can enhance the stability. So, that has been reported by the various research paper that can be published in the Springer Nature. So, by illustrating the mechanism of the stop band tuning by the counter ions exchange in the various film. So, these are the cross sectional scanning electron micrograph of the dry lamellar, and that has been taken for the American Chemical Society. So, DBRs can also be manufactured by alternating polymers and nanocomposite layers with the different refractive indexes. So, Apart from these solids, we can use the polymers as well as nanocomposite layers for the preparation of the DBR. So, DBR can achieve reflectivity must be greater than 95% and can be processed by solution based methods such as spin coating, dip coating and the doctor plating. So, we can prepare the DBR by these methods. Moreover, polymeric materials with the refractive indexes variable by external physical and chemical stimuli can be used for DBR fabrication with the possibility of the finally tuning the spectral features of the stop band. So, the wide variety of the organic material that could be utilized for the realization of the quantum batteries, and this has been recently explored by the various scientists who experimentally demonstrated the concept of quantum batteries using a microcavity in which the active material consists of organic material. So, Lumogen F or orange, that is LFO, that dispersed in a transparent PS matrix. You can see here, this is the schematic of the microcavity with LFO molecules, and absorption, we are having the red line and the left vertical scale, and the PL, that is the blue line, absorption and photoluminescence. So, we are having the blue line right vertical scale, the spectra of 1% LFO in the PS film. So, LFO absorption and the photoluminescence spectra are basically define the operation in the vicinity of the 0,0 electronic transition, which is the transition between the lowest vibrational state of the ground and the excited electronic states. The LFO molecules can be regarded as TLS. So, the number of coupled TLS was controlled by regulating the concentration of the dye molecules. So, charging and energy storage dynamics were characterized by ultra fast transient absorption spectroscopy. So, charging and energy storage dynamics were characterized by the ultra fast transient absorption, that is TA spectroscopy. So, we can find out all the parameters through this ultra fast transient absorption, that is TA. In the ultra fast transient spectroscopy, the sample under study is excited by an ultra short pump pulse, as we are using the light photons. So, here we are using the ultra short pump pulse and the energy stored in the sample, which corresponding to the number of the excited dye molecules, and it is measured by a transmission changes of a second ultra short probe pulse whose temporal decay with the respect of the pump, that is the tau, and is controlled by the mechanical decay line. So, you can see here that is an example of the ultra fast transient absorption spectroscopy, where a large pulse, that is defined by the green, excites the LFO molecules whose energetics are measured by the delayed probe pulse. You can see here that is a probe delay, and left hand side we are having the energy, how it is delaying. So, that is a molecular excitation, and that is a delay that will define a laser pulse excites the LFO molecules. So, the measurement allows the rise time, that is defined by the tau, and the peak energy density, that is defined by the E maximum, and the peak charging power, that is defined by P maximum, to be estimated by using these graph. So, now you can see the experimental setup which is used for ultra fast characterization of the sample reflectivity. You are seeing here that there is a various arrangement where we are having the beam simplifier, beam splitter, we are using the probes, we are using the chopper, we are using a delay, we are using the detector, we are using the microcavity, as well as there is a various diagram. So that compares the temporal dynamics of the energy density in the microcavity, which is proportional to the del R by R tau for the difference loading with the LFO film concentration varying from 0.5 to the 10%. In all microcavities, one observed that a fast rise of the signal and followed by a small decay. So, fast rise, small decay, that represent the fast charging and small discharging. So, time resolved energy density of the microcavities that define, and that shows the concentration of LFO and the photon density that is defined by R used for each sample. So, in all microcavities, one observed the fast rise of the signal followed by the slow decay. By analyzing the data, taking into the account the instrumental response function. So, the researcher demonstrate that as a number of molecules in the microcavity increases, its charging power density remarkably increases. So, the super extensive property means that it takes less times to charge a single microcavity containing n molecules than it would be charged n microcavities, each containing a single molecules, even if the latter were charged simultaneously. Furthermore, one microcavity of n molecules will store more energy than the n microcavity each of which contains a single molecules. So, that is the basically define the quantum batteries. So, further in the next lecture we will discuss the other type of quantum batteries. Thank you very much.